So here's a problem of a type you should be able to do for the gateway. Integrate x over x squared plus x minus 12. This is an integral of what's called a rational function. Notice there's no square roots now. This is a simpler kind of function. It's a ratio of two polynomials called a rational function. And when the bottom is something that can be factored using real numbers, which it can be in this case, as x plus 4 times x minus 3, that's a hint that partial fractions can be used. And if the numerator of this rational function has a degree less than the numerator, the degree of the denominator, if the top has a degree less than the degree of the bottom, which it does, the degree of that is 1, highest power of x, the degree of this one is 2, you can use partial fractions right away. If the degree of the top is the same or higher than the degree of the bottom, which is going to be the next example we'll do, then you actually have to do long division first before you use partial fractions. And it's the long division that doesn't show up in the gateway. You'll be happy to hear. Okay? But it's something you should be able to do on homework because sometimes it's necessary for applications. So what is partial fractions? What we want to do is we want to take this fraction and break it apart into two fractions that are simpler. Partial fractions. How? Can we reverse the steps of adding two fractions? When you add fractions, you have to get a common denominator. This denominator, the bottom of this fraction, is the product of two things. Maybe these two fractions should have those things individually as denominators. Right? If you add two fractions like this, the common denominator would be this product, x plus 4 times x minus 3. And if you made the numerators constants, call them capital A and capital B, think about it with me here, and you tried getting a common denominator of x plus 4 times x minus 3, with this fraction, you'd have to multiply the top and the bottom by x minus 3. And with this one, you'd have to multiply the top and the bottom by x plus 4. In both cases, the numerator would then involve x, a first power of x, and possibly it could simplify to just x if the constants canceled. That's the intuition behind why this might work. And it does work. You've got to solve for a and b. You got to figure out what they are. You want this equation to be true no matter what x is. You want these to be equal functions of x. As long as you're not dividing by 0, which will introduce something confusing, but hang on here. To solve for a and b, what you want to do is simplify these so there's no more fractions. Multiply both sides by that common denominator of x plus 4 times x minus 3. That dot means multiply. X plus 4 times x minus 3. If I do it to one side, I got to do it to the other. You get complete cancellation on the left of the denominators, leaving you with just x. And on the right, after you use the distributive property, you get partial cancellation. A over x plus 4 times this product makes the x plus 4's cancel, leaving you with a times x minus 3. B over x minus 3 times this, the x minus 3's will cancel, leaving you with b times x plus 4. And remember, your goal is to solve for a and b. You want these to be equal no matter what x is. Now, I'm about to solve for a and b, and I'm purposely going to do it two different ways. Partially to illustrate that you can do it two different ways. Partially to emphasize that the longer way, which I'll show you first, you might say is a little more rigorous. Well, neither way is super rigorous, because we're still got this issue of what happens if you're dividing by 0, but it does work either way. One way, the long way, is to expand this out, multiply the a through the first set of parentheses, multiply the b through the second set of parentheses, and then gather like terms involving the same powers of x. Ax and bx are like terms. Gather those and factor out the x to write it as a plus b times x. And the two terms that do not involve an x are constant terms. Gather those two things together. I want this function of x to equal this function of x, no matter what x is. Since this function of x is really the same as 1 times x plus 0, that means I want to match coefficients. The a plus b needs to equal 1, and the negative 3a plus 4b needs to equal 0. Does that make sense? I want these to be equal no matter what x is. The only way that's going to happen is if the coefficient of x here matches the coefficient of x there, which is 1. And if this constant term matches that constant term, which is 0. So this gives me a system of linear equations in a and b. A plus b must equal 1, and negative 3a plus 4b must equal 0. If you like working with matrices, you could write that as a matrix equation, or make what's called an augmented matrix and do row operations to solve for a and b. If you have no idea what I'm talking about, don't worry about it. What's probably simplest is to, for example, solve this equation for, say, b in terms of a by subtracting a from both sides, then substituting that into the other equation in place of the b. Solve for a, negative 3a plus 4 minus 4a equals 0. So negative 7a equals negative 4, and a is positive 4/7. Tracking with me there? Just algebra, I distributed the 4 through there. Negative 3a minus 4a is negative 7a. I subtracted 4 from both sides. And then I divided both sides by negative 7. Negative 4 over negative 7 is the same as positive 4/7. Go back up to that equation. Substitute in for a to get b is 3/7. So that's the maybe slightly more rigorous way to do it, but it takes a little while. There's a much quicker method. And that's to come back here and say, I want this to be equal no matter what x is. So why don't I just pick a couple of values of x? Oh, how about 3 and negative 4? To make these respectively 0, and I'll get simple equations to solve for a and b. They'll practically be solved already. See what I'm saying? If I take this equation and say, let x equal 3, then it becomes 3 equals a times 3 minus 3, which is 0, plus b times 3 plus 4, which is 7, and therefore b is 3/7 right away. And if I take this equation and let x equal negative 4 to make that 0, then I'll get negative 4 equals a times negative 7, right? Negative 4 minus 3 is negative 7, plus b times 0, and a will be negative 4 divided by negative 7, which is positive 4/7. Same answer is much quicker. You might be disturbed by this because 3 and negative 4 make the original equation undefined. But don't worry about it, it works. couple times in this class recently, the ends justify the means. It's not a way to live your life, right? The ends do not justify the means in life. But sometimes in math, they do, if we're not too worried about things. Maybe not always, because maybe you're missing something. Maybe it leads to some sort of error if you think the ends justify the means. But here it works. So what has all this gained us? You might have been wondering why we were doing this in the first place. Trying to integrate. Trying to integrate this function, which means I'd be integrating this sum. And if you think about integrating those two functions, they're both easy to integrate. The answer is going to involve natural log, right? If you want to integrate something like that, if you want to be careful about it, you could let w equal x plus 4. You'd be integrating a over w. dw would be the same as dx. You get a times the natural log of the absolute value of w, which is a times the natural log of the absolute value of x plus 4. Similar kind of thing there. That's why we're doing this. Makes the integral easier to do. And that's how we will now finish it. Come down here. Our integral now becomes this integral. A is 4/7, B is 3/7. And that's something you can do in your head. 4/7 times the natural log of the absolute value of x plus 4 plus 3/7 times the natural log of the absolute value of x minus 3 plus c, done. This type of problem shows up in the gateway. So you need some practice. The assignment due Friday will have some practice. It's best to leave on the gateway your answer like this. For the purposes of application, sometimes, like in differential equations, you might want to use properties of logarithms to rewrite it. But do not do this on the gateway because you might make a mistake. For example, the coefficients in front by a property of logarithms can become powers inside the logarithm like this. And then when you've got the sum of two logs, that's also the same as the log of the product. So I can write ln of the product of those two things. And actually x plus 4 to the 4/7 power in x plus 4 absolute value of the 4/7 power is always going to be well, if I get rid of the absolute value signs, what I'm trying to say is you can get the same thing. Because the 4 being an even number is going to make this a positive quantity, even when x plus 4 is negative. With the 3 being an odd number, I technically still need the absolute value signs here. And since raising to the 1/7 power is the same as the 7th root, I could also do this. Okay, I could write a 7th root in there. Okay, so these are just a bunch of different crazy ways that I could write this function. You don't have to do that in your homework or the gateway. And for sure in the gateway, leave the answer like that. On to the last problem, which is another partial fractions problem. But I'm going to make, well, I'll make the denominator the same, x squared plus x minus 12, but I'm going to make the numerator different. I'm going to make it the x cubed. Now we're in a situation where the top, the numerator, has a degree 3 greater than or equal to the degree of the denominator 2. You got to use long division first. And by the way, that would happen even if it was x squared on top. Same degree. You still need to use long division first. I'm taking x cubed and dividing by x squared plus x minus 12. That means for the long division symbol, the x cubed goes inside and the x squared plus x minus 12 goes outside. You want the higher degree thing, possibly higher degree thing, inside. That's from the thing on the top. And the thing on the bottom, outside. By the way, you'll see in the book some examples where you have a rational function and the bottom of the fraction is not something you can factor. It's called irreducible. And you'll see examples where the book completes the square first before solving the integral. And they don't use partial fractions. They actually use a trig substitution. I'm not doing an example like that today. Probably do one example on Friday. I need to ask, what do I multiply x squared by, the highest power by, to get x cubed, the highest power there? I need to multiply by x. Put the answer up there. Then take that x and multiply times each term here, putting the answer down there underneath the x cubed. X times x squared is x cubed. X times x is x squared. X times negative 12 is negative 12x. Then subtract. There's something called synthetic division where you add, but with long division, you subtract. X cubed minus x cubed is 0. 0, which you don't see, but pretend it's there, minus x squared is negative x squared. 0 minus negative 12x is plus 12x. You don't have to think about the zeros, actually. You could just imagine distributing the minus sign through there. Okay, what does this mean? If whatever you get here has a degree less than what you're dividing by, you can stop. It doesn't. It has a degree equal to what I'm dividing by, so I can't stop. Continue. What do I multiply x squared by to get negative x squared? Minus 1 is what I do. Now take that minus 1 and multiply times each term, putting the answer down here. Negative 1 times x squared is negative x squared. Negative 1 times plus x is minus x. Negative 1 times negative 12 is positive 12. Careful though, I am subtracting. Negative x squared minus negative x squared is 0, because the two minus signs make a plus. 12x minus negative x, careful, is 13x. And effectively 0 minus 12 is minus 12. Now I have something whose degree is smaller than what I'm dividing by. I can stop. That's the remainder for the division. This is the quotient up here. Quotient. This is the remainder for this polynomial long division. What does all this mean? It means x cubed over x squared plus x minus 12 is the quotient x minus 1 plus another fraction with the same denominator as before, x squared plus x minus 12, but whose numerator is the remainder. In this case, that's 13x minus 12. The analogy with numbers works like this. If I, for example, am doing 25 divided by 6, you learned in 4th grade that the quotient is 4 and the remainder is 1. What does that mean? It means 25/6 as a fraction is 4 1/6, because it's 4 plus 1/6. There's the quotient. Quotient. There's the remainder. And then you say this improper fraction 25/6 equals this mixed fraction 4 1/6. But what is 4 1/6? It's 4 plus 1/6. That's a sixth thing. Same idea here. There's your quotient. There's your remainder. And why is this good? Because now I can integrate this function by integrating that function. This part's easy. That part can be done with partial fractions. Mm-hmm. Are you saying to factor this? Or that's what I'm about to do, is factor that, if that's what you're really asking.
I meant like at the first part.
Factor it right away. It's better to just leave it like this so you can do the long division easier. I made the bottom the same as the previous example. It can be factored as x plus 4 times x minus 3. And once again, you can get away with constants on the top in both of these fractions, but they're going to be different constants than the last example. This is the partial fraction step now. Going to go a little quicker this time. And I'm going to use the shortcut. Multiply both sides by the common denominator of x plus 4 times x minus 3 to get complete cancellation on the left and partial cancellation on the right. This fraction that I'm pointing at times x plus 4 times x minus 3. The x plus 4's cancel, so you have a times x minus 3. And with the other one, the x minus 3's cancel, so you have b times x plus 4, just like before. It's the left side that's different. The shorter method says go ahead and let x equal 3 and negative 4 and see what happens, because these will be 0. If x is 3 on the left, 13 times 3 is 39, minus 12 is 27, equals a times 0 plus b times 7. So b is 27/7. And if you let x equal negative 4, to make that one 0, right there. On the left, 13 times negative 4 is negative 52, minus 12 is negative 64. A times negative 7 plus b times 0. So a is 64/7. Almost done. This all means then that my original integral is, don't forget about the quotient. Don't forget to integrate that. You get it wrong if you forget that. Integrate x minus 1. That'll be 1/2 x squared minus x. Integrate 64/7 over x plus 4. You'll get plus 64/7 times natural log of the absolute value of x plus 4. Integrate 27/7 over x minus 3 gives you plus 27/7 natural log of the absolute value of x minus 3. Don't forget your plus c. Amazing. It's like magic. Woo. You never guess you could do it ahead of time unless you have the experience. And even if you know you could do it, you never guess what the answer might be ahead of time, although you might know it involves logarithms. Check it quick with Mathematica. Remember, LOG in Mathematica is actually natural log. And it looks like we got the right answer. You don't forget the plus c, though. Okay? Integration is definitely harder than differentiation. Keep practicing. See you on Friday.